Greetings. I haven't posted in a while. Apologize. I'd like to say there was some good reason. Luge lessons in Rangoon. It's an Austin Powers reference. But no, I just got bored. And what I was working on, I think the last video, I think I put out a video with this, was these two coils that are wound at right angles. There's a coil going around like my middle finger there, and then there's this one that's going like that, and on the two ends here are ceramic magnets, and when you pulse this one you get something off of this secondary, which normally if you don't have the magnets there and you have two coils at right angles, they cancel each other out entirely and you don't get anything off of the secondary. So what I did that I haven't made a video of is, and I wound this one, which is a bit bigger, and I replaced the ceramic magnets with toroid, just toroid cores. So there's a toroid core here and a toroid core there. There's a lot of interesting stuff here. For one, the LCR meter says this has an absurd Q factor, like 200. I don't believe it. I think it's confused by the geometry. The other thing is that, as with the magnets on this one, just getting rid of the magnet part and just having a ceramic core, I mean a ferrite core here and here, you still get something off the secondary. This one actually worked better than that. Then I have some larger magnets. It's still minuscule. Even though it's minuscule, maybe I'll make a video as we get to here. I'm not going to make any promises on that. Maybe we'll make a video on this, maybe not. But there was a little bit more off the secondary. It's still very small. It's still, when you loaded the secondary and like pulsed this with a cap, you still couldn't see any deformation of the LC oscillation. So it's sort of, you know, I bet you could improve on this. The problem is it takes a long time to wind these in and out and in and out. Like, you got to thread it through. You got to wind the wire on here and then thread it through like you're crocheting. So I was trying to like get interested in, you know, well, if I put more winds, if I put less winds, if I, you know, I've got some big ceramic magnets, will that be different? And it's just like, it's worth doing, but I don't feel like doing it now. So it's all right. I'm finally a little bit enthusiastic again. So what is there to work on? So if we go now to the electronics tutorials website, which I used to rave about incessantly. It's still, I would say, a very good website. But there were two videos that I'd said in passing, oh, I'll make one of those. One was showing what I did with Grok and integrating this equation. And the other was looking at the size of the air core for an inductor, a single layer inductor, and the induction that you get. And that was because I used the equation for that off of electronics tutorials, and I was so excited. I 3D printed all these things. I had this whole idea of this like radiator type coil, and then I started to put it together and it looked nothing like their equation. And then I went to a couple other sites and they had a different equation. So the equation for the induction of a single layer air core on the electronics tutorials website is dead wrong. And as I said, I was going to make a series of videos on that, but I was like so pissed off, you know, pardon the French, that I didn't get around to it. But I'll try and hopefully say something more on that and tell you exactly what happened. But in general, they're very, very good, and I've learned so much from them. So the inductor, the LR series circuit is what we're interested in. And here's that equation that I was talking about. The current in a given inductor at time t is equal to the voltage divided by R, 1 minus Euler's number, if that's how you say it, to the negative RT over L, and that gives you your amp flow at any given time for any given inductor with a given voltage, resistance, and induction. So as I was getting at, if you have a given coil, you can know what the amp flow is at half a millisecond, at a millisecond, at 2 milliseconds. It's going to be changing all over the place until the coil saturates and the current flow becomes constant. So it's a much more difficult question to say how much current flowed in the first 2 milliseconds. And I'm sure all of my viewers would, walk in the park to integrate this. It sounds like, I got no freaking clue how to do that. Maybe I'd have a chance if I spent a month back on the calculus textbooks, or maybe I get lucky and it would be faster than that. But it's not a straightforward thing for me, and I think for most people. So here's the history of this chat I had with Grok from February this year. I'm saying, "Hi, Mr. Grok. I'd like your help with the math problem." I think it's a good habit to be polite to these things until we know what they are. Just saying. And he says, "Oh, I'm happy to do that." And then I asked, "Can you review the contents of a web page?" Because originally, like a few months before that, you couldn't do something like that. But already back then you could do that. So I gave it the URL to the page we just discussed. Here's the here's the URL. Pay special attention to the equation for the expression of the current in an LR series circuit, i.e. the instantaneous amp flow. Do you see that? And it gets back to me. Yeah, I've reviewed that, and here it is. Here's what each term means, and goes on about that. I say, if one wished to know the total amount of charge into an inductor, one would wish to integrate this, right? It says, "You're absolutely on the right track." How nice of it. And from there, I didn't even have to ask it to do that. I just mentioned, isn't that, you'd want the integral to get that. It says you're on the right track, the current equation, and I've used this dummy variable t, and now let's break the integral into 2 parts. First term this, second term that, going. Multiply the constant. I don't know what the heck it's doing. But at the end of it, it comes up with this equation. Q, amount of charge that's floated in a specific amount of time, is equal to that. Now, the interesting thing is if you put that in a spreadsheet, you get really reasonable answers. So I guess I'd back up and say, I don't know if this is nonsense or not. I'm not a good enough mathematician to know if it did it correctly. But if you put it in a spreadsheet, you get correct answers, seemingly correct answers, and you can kind of approximate whether they're correct, because we talked about you can use the spreadsheet to say, all right, you can figure out how much current flowed in 25% of the time and 50% of the time, 75 and 100. Add those together, and the more divisions you have, 10, 20, 30, 40, 50, whatever, then you're gradually approximating this equation. And so this is correct. And so now you can just have this equation in your spreadsheet to know how much current flows through an inductor in a given amount of time. And so I kind of went about this a little backwards. So I'll tell you another weird thing that happened here. So it came up with this equation, but for some reason I didn't see it in the history, but a couple weeks earlier I'd asked it the exact same thing, and it came up with, where is it? It came up with this equation. So the first thought is, oh no, there's this equation for instantaneous amp flow, and there's this equation for instantaneous amp flow. So what I did here was say, look at that equation. And this was Grok that did both of these within like a week or two, and it did it different ways. And I said, are the two equations equivalent? And let's dive into this intriguing comparison. So it went through it all, and at the end it says, yes, the equations I gave and the rearranged form are the same. They're just different arrangements of the same equation. That's like mind-blowing to me. It solved it differently 2 different times, like a week apart. And if you put the 2 equations in a spreadsheet, you get the same answers. So I'm saying that's super, Mr. Grok. And yeah, man, these things are scary. Or perhaps I should call you Dr. Grok. And it, you know, he's like getting the joke. I'll take it as a compliment. So just to continue on with this, the next thing I thought was, all right, so now we know the charge expended into an inductor in a given amount of time. For that same time interval, can you calculate the energy in joules that are expended into the coil, which is a similar kind of issue that you need to integrate for that. And so, of course, it came up with that. I'm sorry, with this equation for the energy expended into the coil in a given period of time, not the charge. And then just for the heck of it, I was looking at the total energy expended in the coil and the total energy stored in the coil over time, which I kind of knew the trend that I expected to see, and it nailed it. You know, here's time 0.001 for this particular inductor that I gave it the parameters for. The energy stored is that many joules, the energy expended in is that. But here, after you've gone out to where the coil is entirely saturated, you know, you have 2 stored versus 196 versus, you know, let's forget the zeros, 48 versus 49. And there are a lot of you know, relationships there with the Q factor as well, in terms of, you know, with a good Q factor, you're getting closer and closer to that being unity. So this was all great, and then I thought, well, you know, now I can just, let's see what happens if you know, you're running at like 50,000 or, you know, 5 million volts, and, you know, I don't need to do anything. I can just plug it all into the equations and see what comes out. And I did one with very high voltage here, and it came out with total energy supplied is this, and the energy that you end up stored in your inductor is that. And so for like 5 seconds I was like, holy shit, you know, that is just high voltage. And then I thought about it another 5 seconds. It's like, no. There's something screwy here. So I put the equations that Grok had derived into the spreadsheet, and you know, calculated from the spreadsheet total energy supplied, total energy stored in the inductor, and I came up with something entirely different. So this was at 20,000 volts. So at this point, I'm pretty sure I already knew it was wrong. I was saying, oh, this is just dandy. Now let's look at all 6 time intervals, and I was seeing like what it's going to come up with there. And it's, you know, it was again off. I was saying drop the voltage. I was trying to see if it was going to notice anything. So here I was thinking, well, maybe I've asked too many questions. So I'm saying, is there an ideal number of questions before? I mean, I knew it was off there, but it didn't. And it's saying, no, you can ask as many as you like. So here I directed it to where it got it wrong. I said, Grok, please double check this something for me. This is a calculation of the coil done at 20,000 volts. There's the pulse duration. Total energy supplied was this. And So let's double check that. Yeah, everything lines up correctly. And so then I had to just come out, and it does this whole like pages of like, yeah, everything's fine. And then I say, isn't 200 million times this equal to that? Not what you're saying. What am I missing? And so it goes, you're absolutely right to question that, and I owe you an apology. I slipped up there. Let's sort this out together. And it goes on, I botched the final multiplication. You caught it. You caught it perfectly. So it ends with that. Sorry again for that. Your sharp eyes saved the day. So what I'm saying is it's an incredibly powerful tool, but you have to be able to have a reference back to reality, because it will also just make up stuff. And once it's made stuff up, as I pointed out, I'm like pointing at it, double check this. Yeah, that's right. Until you actually say, no, it's not right. And then it gets it. So I guess what we'll do, since I've been talking at you for a bit, is stop this video here. And I don't know if people were bored to tears or enjoyed this, but I can go on and point out in the next video, because I need to order the 1-inch ceramic magnets, and they'll take a few days to get here. This is the first video that I said I'd make. The second video was the one about the core, the air core size and induction, and the equation on what do you call it? Electronics tutorials was flat out wrong. But I can tell you that I didn't know how you might actually use that integral for the equation for instantaneous amp flow until I started thinking more deeply about the pulse motor. And I can tell you that with that equation, you could figure out then, for a given coil with a given induction and a given Q factor, you could figure out the exact RPMs that you want to run the thing at in order to get the most energy back from your spike. And without this equation, it would actually be kind of difficult. So it did turn out to be useful. And there's another part to this, which, if people enjoy this, I can go into, is I thought I'd make it, it can like look at things and say what they are, like, oh, that's a pine tree or whatever. And so you can send it, for instance, I have a coin collection. You can send it photos of coins and say, how much is this coin worth? And it'll return something. But what I ended up, and that idea is still kind of in the back of my mind, but what it ended up doing was just making up coins out of whole cloth. Like, it didn't get the files, and it's telling me that's a 1973, Lincoln penny. It was minted in Philadelphia. It's got a little scuffing around the edges. You kind of be like, Grok, you actually didn't get the picture there. You're just making this up. So, I have to laugh because it's just so bizarre. But yeah, it is one scary powerful tool. And I'm going to make use of this equation for instantaneous amp flow as we build the integral, as we build the Adams motor coming up. So back at you with more later. Thanks for coming along. Bye.